Okay, we'll try that. We might have to play around with it a little bit. I'll just turn the front light off as while we're discussing the syllabus and stuff. Okay, so this is Physics 3300. Is everybody in the right place? Okay, great. So it's intermediate physical oceanography. Usually this course is taken by many people who are in the Ocean and Naval Architectural Engineering program, and then also by some people who are in the physics program. Could you put your hand up if you're in the Ocean and Naval Architectural Engineering program? Okay, so it seems like there's a spatial gradient happening. So how about physics? And are you physics proper or you're geophysics? Okay. And everybody else is straight physics or geophysics? Straight physics? No? Some third option for you?
Environmental physics.
Environmental physics. Okay, cool. Great. So my name is Joe. I have been teaching this course now. This is my 4th time through, but it's changed a little bit each time, so it might not be as polished as some other courses that have been taught for that amount of time. The course website is on Brightspace, so everybody knows how to find that sort of thing. So right now the syllabus, I'm going to go through the syllabus today, but the syllabus is also posted on Brightspace, as are the course notes for the first section of the course. So I'm currently trying to type up as much of the notes as I can, because as you'll see, my handwriting can sometimes be difficult to read. I will do my best, but as a general rule, if I'm writing something on the board and you can't make out what I'm writing, please just like shout out and I'll try to explain as well as I can. My hand just gets tired after writing for an hour. And it's also weirdly bad even at the beginning of class. Okay. So I think maybe I'll just start off by going through the syllabus, and then we can see if there's any questions or anything like that. So just have this little welcome to the course. So if you want to find all of the content for the course, so it's all just going to be under content, and on the side I have syllabus and then course notes. So right now, it says course notes version 1, and so if you click on that, you'll get a file, and we've got lots of notes. But these notes are in progress, and so there might be stuff in there where like a sentence ends halfway through or whatever. And so I'm going to be updating this and I'll update the version numbers also. So I'll try to be clear when it comes around time for midterms and stuff, like this is the final version of the notes that's going to be covered, that sort of thing. For the syllabus, we have it here. I'll just bring up this copy. Okay. So as I mentioned, my name is Joe. One very important thing is probably most people at some point in this course will want to send me an email about something like extension of an assignment or a question or whatever. So I don't really use the Brightspace messenger. So if you send it to me on there, there's a chance I'll see it, but there's also a chance I won't. So the best way to reach me is emailing me at this email address. The key thing is that it's JG Fitzgerald. My middle initial is G. Every time I teach a class, somebody leaves out this G, and then they say like, hey, I sent you an email a week ago and you never responded, but it's just because I didn't get it. So generally, if I don't respond in a couple of days, I'll usually get back to you within a few days. So if you haven't heard from me in 4 or 5 days, like something has gone wrong and I probably didn't get your email, so just follow up with me or maybe check the spelling. I'm not going to have any set office hour, but I'm pretty available by appointment. So if you want to talk about anything, go over a midterm, questions about the assignment, just email me, and I'm happy to set up an appointment. The prereqs are some kind of background in fluid physics and calculus, and I think for the engineers, there's a whole totally different structure, and the prereqs work differently, and you guys are all familiar with that. Okay, so the evaluation scheme is very, very interesting to everybody. So there's going to be 4 assignments. Those are worth 5% each. 2 midterms worth 20 each, and then the final exam is worth 40. On the assignments, nowadays it's important to mention something about AI and collaboration, how all that stuff works. So on the assignments, you are perfectly, you're encouraged to work together if that's helpful. And in terms of AI, if you want to use AI to like help you understand the concepts and like learn about the question and maybe figure out some strategies for how to do it, that's perfectly okay too. The only thing that's required is that when you submit work for grades, it has to be your own work. So you have to like write up your own solution. Maybe like read the ChatGPT thing or whatever, and then like write it up for yourself, make sure you understand all the steps. And then I would just call that learning the material, right? So I have no problem with that. But you can't hand in stuff that was just generated by AI. Okay, so I made up a schedule for the course that we will try to stick to. The tests very likely are not going to move. So the two-term tests are scheduled now for February 12th and March 19th. The assignments sometimes can drift around a little, but roughly speaking, these will be the timings. And so generally you'll have about 2 weeks to work on a homework, and the homeworks will be maybe 4-ish questions. And the way the course is structured is that there's, roughly speaking, 2 assignments and then a midterm, and then 2 more assignments and then another midterm, and then the final covers the last bit that wasn't covered on either midterm. Okay. Any questions about the scheduling or evaluations or anything like that? All right. So physical oceanography is a very broad topic. And that's really true of any of the sort of atmosphere, ocean, climate science topics. And they all kind of get lumped together or broken apart in different types of courses. And so exactly what would be covered in a course called Intermediate Physical Oceanography is really pretty arbitrary. So if you're at a different school, you might get different topics covered in different courses. Generally, the whole slate of topics would be covered across several courses, but the individual distribution within a stream of courses is very varied. And so what we do here is that we have 3 oceanography courses in this department: Introduction, Intermediate, and then Advanced. Some people I know have taken the introductory course already. So the introduction course is very it's like a survey course with like very few equations, broad overview of phenomena, and it covers like the whole global climate system. So from oceans to El Nino to monsoons and Gulf Stream, all over the world. This course is very different, and this is sort of a fluids first introduction to physical oceanography. So the point of view that's taken in this course is that to understand the physics of the ocean really requires understanding of fluid dynamics. And so we're going to start this course with mathematical background that's needed for that, and then the first significant portion of the course is the fundamental equations of fluid dynamics. And so you might have heard of this equation called the Navier-Stokes equation. Can you put your hand up if you've heard of that equation before? Lots of people, but not everybody. That's okay. So we're going to derive the Navier-Stokes equation, learn how to use it, but the course is designed for people that have not fully taken a vector calculus course, right? So I think, so who here has taken vector calculus before or is taking it now? So you guys are all taking it now, right? And do you guys have it already, or yeah, okay. All right. So we're going to teach so all the vector calculus concepts that are needed are going to be introduced as we go with examples. But there's just no way around it. So, fluid flow in the ocean happens in 3 dimensions, and it's a function of time also. And so you just necessarily need vector calculus to understand anything. So we're going to start out with math, and then with the equations that underlie fluid dynamics. And then the rest of the course is really about applying those equations to understand different phenomena that are relevant to the ocean. And so the course is going to focus a lot on waves. There's a ton of physics that is connected to waves in the ocean and the atmosphere. But I don't just mean surface waves. So the waves that we're very familiar with and that are quite important for certainly motion of ships and design of ships, stresses on ships, we think of the waves on the surface. But there's all kinds of other waves, including sound waves. Sound waves are very simple, relatively speaking, and so we're going to start with that. We're going to start with sound waves in the atmosphere and ocean, and then move on to understanding the mathematical properties of the surface gravity waves, or the classical waves that we all know, And then depending on how much time we have at the end of the course, there are some bonus topics such as internal gravity waves. So you might not be aware of this, but so when we see waves that are on the surface of the ocean, there are also waves that are much like that, but they're not at the surface. They're propagating in the interior. And they can be much, much larger than surface gravity waves. They're very interesting and have a big effect on ocean and climate. And then if we get time towards the end, a special topic of Fourier analysis. This also might overlap. I know the naval architecture people are probably taking this course vibrations as well at the same time. Is that right? So many of these topics will have some overlap with that quasi-notorious vibrations course. Okay. There's no book, so I don't use any book. But the notes and the assignments should be really self-contained. If you do want a reference, though, there are many good books on physical oceanography that take this sort of fluid mechanics perspective. A pretty good one is called Introduction to Physical Oceanography by Stewart, and this is just available online. So it's just a free ebook, and it covers many of these topics. I'm not sure if it gets into sound waves in as much detail, but certainly surface gravity waves will be covered. And you can take a look at the rest of the syllabus for comments on AI, missed evaluations. If you have to miss something, I'm generally pretty flexible with due dates and stuff like that, much less so for midterms, obviously, but if you need an extra day on an assignment or whatever, I would much rather you take the 2 extra days you need and try to work on it than just skip it because you don't have time or whatever. And I understand that everybody's really busy, and sometimes things, your schedule might not be able to line up with the course schedule. And so if you need any kind of accommodation like that, just let me know. Okay. All right. Does anyone have any questions on the syllabus? The course is mostly going to be taught on the board, and by mostly I mean probably everything except for this syllabus. But the lectures are going to be recorded. I don't know how well I'm going to try to work on figuring out how well you can see the board from this vantage point here. But in any case, there will always be the verbal explanation, and then you can look at either your own notes or the notes that I'm going to publish or put on the website rather. And so between the verbal explanation and the notes, you should be able to piece it together, even if you can't necessarily see what's written on the board. Okay. And of course, this is everybody's favorite time slot in the whole schedule is 3:30 to 4:45. It's nice because that way you really want it to be dark when you're going home. Just make sure that you have no happiness in your life at all. Okay, I will stop it there. So if no one has any questions, we can just get going. And today we're just covering math review, and a lot of it is mostly just a set notation and things like that we know what we're talking about when we use different symbols. Okay. Oh, one other thing. So the course has some coding aspects. So can you put your hand up if you're familiar to some degree with Python, like you've used Python for something before? Okay, so do you have it on, does everyone have Python on their computer? Or have access to a computer that has Python? Okay, so usually, so this course is not a coding course, it's a course about understanding ocean physics. But as I'll mention, sometimes when you're studying a subject that is pretty mathematical, you run into equations that just can't be solved exactly. There's just the answer isn't just cosine or something, it's something you can't write down. And so you have to do the solutions on the computer. And other times you may be able to work everything out with pencil and paper, but it might be so laborious, the expressions are so long that it's actually easier and better to just do it on the computer. And what I'm going to try to do for this course is that for the coding aspects, I'm going to provide a Jupyter notebook that sort of lays out the problem, but for another example. And then what you have to do is like change the code so that it matches the example that you have to do on the assignment, for example. And I'm hoping to avoid you guys spending too much time stuck on like, is there a comma missing and stuff like that from your code. At the same time, we all know it's very, very easy now to use ChatGPT to write simple codes to do anything. And I don't even mind, if you use ChatGPT to help you write the code. The key thing is to actually try to read what it produced after it gives you some functioning code, so that you can understand how it actually works. And that'll just be helpful. Anybody doing any kind of modeling related to shipbuilding or physical research or anything like that, you're going to have to use these types of Python-based techniques at some point, and so learning how to use them is a good idea. That being said, there's not going to be any like coding, like write this code on the midterms or anything, so it's not that kind of course. Okay, so we can start off with mathematical background. So here what we're really trying to do is set our notation and sort of remind of calculus and vector concepts. Okay, so first thing is the coordinate system. So if you want to study the ocean on the scale of the whole planet, so you want to be writing or doing some analysis that like simultaneously involves the Pacific Ocean and the Atlantic Ocean, for example, then you would typically use spherical coordinates, right? Because the Earth is a globe, and so the Earth is a sphere, rather. So the appropriate coordinate system would be spherical. However, for this course focuses on smaller scale phenomena that are more relevant to, say, coastal or naval type applications. And so for us, so we're not going to deal with global topics like thermohaline circulation or El Nino, things like that. In this course, those are covered in other courses. And this course is more about an introduction to fluid dynamics and applications that are sort of more local. So if you're, and a particular thing that means is, in this course, the Coriolis effect and the rotation of the Earth is not going to be discussed much. Whereas in other courses, that's very, very important. Because on the global scale, the Coriolis is really, really critical. But on the scale of St. John's Harbor, it's not very important at all. So what we're going to use is almost exclusively, we will use Cartesian coordinates. And there's a little bit of notation and naming here. So generally, if we have an ocean, so we say that's the bottom of the ocean. When I draw those dashed lines, this means that's the bottom. We have some waves on the top, maybe. So what we do is we'll say our XYZ coordinate system looks like this. We have X is one of our horizontal coordinates, Y is the other horizontal coordinate, and then Z is our vertical coordinate. And we always define Z equals 0 as being the surface of the ocean. And so this is something it's almost for sure going to trip everybody up at some point. But so we want to have our coordinate system so that going to more positive values of Z means that you're going up. So if the number Z is increasing, it means you're going up. Which means that down here at the bottom, we define that as Z equals minus H, where H is the ocean depth. And that's typically on average around 4,000 meters or 4 kilometers. and then z greater than 0 is then in the atmosphere. So we're going to be dealing with our vertical coordinate, where in general, when we talk about the location of any object, we'll say like z equals minus 10 meters, which means that's 10 meters below the surface. And so z equals 0 is always the surface. Two other little pieces of notation or naming is that because we don't worry about rotation too much in this course, the difference between east-west and north-south is not too important, but it's still useful to have in your mind what different directions correspond to. And so generally, x is going to be our east-west direction, and that in meteorology and oceanography is referred to as the zonal direction. So that's just slang in this area. Zonal means east-west. And then our y direction is going to be the north-south. And that is called meridional. Okay, we won't use those terms all the time, but it's good to know them. So in physics, we deal with vectors all the time. And so we're going to be dealing lots and lots with vectors in this course. So vector is so it's a quantity or an object that has magnitude and direction. And mathematically, they are columns of numbers. And we denote them by the vector symbol. So for example, we might have a vector v, and we use this little half arrow symbol to denote that something's a vector. And the type of course notes, I don't use that arrow symbol, I use boldface font. So you see something bold, that means it's a vector. And we represent these mathematically by columns of numbers. And so we might have the vector, for example, 1, 0, minus 2. And this would be a vector in 3 dimensions, because we have 3 different numbers. In this course, we're going to switch back and forth, depending on what particular problem we're interested in, between looking at 3-dimensional vectors and 2-dimensional vectors. Some phenomena in the ocean can be understood just by thinking maybe in the xy plane, like maybe there's no vertical component to it. And then other things will be fully 3-dimensional, and so we use both 2-dimensional and 3-dimensional vectors. So we have a 3D vector, and our other vector be 2D, could be something like just 1 minus 1, for example. Okay, sometimes in the notes, and we sometimes just are sort of a little bit sloppy with our notation, and rather than write them as a column, because it takes a lot of space to do that, we write them as like a triple. So like this, can also write V is 1, 2, 3, 1, 0, minus 2, and V 2D is 1, minus 1. And really what I should do is put little transposes here to tell you that they're actually column vectors, but I might not always do that. So just if you see it either inline like that or as a column, that means a vector. When we say, so these 3 numbers, or these 2 numbers, how does that correspond to magnitude and direction? Well, these vectors exist in the 3D Cartesian coordinate system that we're using. So if we have an example, say our vector here, v2d is 1 minus 1, then in our Cartesian coordinate system here we have x and y. Our x component is the first element, so this would be called our x component, that's our y component, and that's our z component. And we have a 2D vector, we almost always mean xy, very rarely do we mean xz. And so we have a vector like this, 1 minus 1 in the 2D plane. It means we go, in the x component, we go over 1, and then in the y component, we go negative 1. So this would be our point, and so our vector would be a vector like that. And so, it has a size, which is given by the length of the vector. We'll talk about how exactly that's defined. And then also direction, which is just the direction that it points in the Cartesian space. We'll do a lot of this sketching. So when you start thinking about fluids, we'll talk about this in more detail. A lot about understanding fluids is about being able to visualize how they're moving. And so we're going to do a lot of sketching what the currents look like, sketching how particles that are embedded in a flow are going to move. And so on the first assignment especially, you'll get a chance to play around with some sketching problems, drawing different vectors and things like this. Okay. So we could do various things with vectors. So one important one is the dot product, mostly for setting notation. So the dot product is for two vectors, A and B. So you might have, for example, A is equal to AX, AY, AZ, and B is equal to, or actually I'll use A1, 2, 3. So A1, A2, A3, and B is B1, B2, B3. Then the dot product is A dot B is equal to A1, B1 plus A2, B2 plus A3, B3, which sometimes is written in summation notation like this. The dot product is a way to take two vectors and produce a scalar. So this number that you get out, A dot B, these two things are vectors. They have the vector decoration. But then the result of this multiplication is we take the first element of the first vector times the first element of the second vector, add that to the product of the second elements, add that to the product of the third elements. And then that's just a number. So it no longer has magnitude and direction, it just has a size. And so the dot product takes two vectors and it gives a scalar at the end. The length, also called the norm of a vector, we denote it as the, it's like the absolute value bracket. So it's the same symbol as the absolute value of x. You can call it the absolute value of a, you can also call it the length, you can call it the norm, you can call it the modulus. And this is just defined as being the square root of the dot product of A with itself, which is sometimes just written as A vector squared. That notation's a little bit sloppy because like what exactly does it mean to square a vector? But what we mean is that you take the dot product of itself. Okay. So let's do an example. Okay, so example. What vector in the xy plane gives a ocean current flowing northeast at 5 centimeters per second. Okay. So that's a very typical speed for an ocean surface current. 5 centimeters per second would be pretty normal, not for the strongest currents, but for sort of intermediate ones. So we're looking for a vector. We usually use the term, the symbol U, to be if we're referring to an ocean current. And so I'm looking for a vector in the 2D plane, so a column of two numbers, that would give an ocean current that flows northeast, exactly northeast, at 5 centimeters per second. Does anyone have an idea? What should I put in these brackets?
Times the cosine and sine of 45.
So you should repeat that.
5 times cosine of 45 and 5 times sine of 45.
Okay. So you're using like the general formula
Yeah.
with the trig functions. That's true. So Ben is suggesting here 5 centimeters per second times sine.
Cosine would be the first one because.
Oh, right. Cosine of 45 degrees and 5 centimeters per second times sine of 45 degrees. Now, does anyone remember offhand what those sine and cosine values are? It's the same number.
Root 2.
One of root 2 over 2 or 1 over root 2, either way it's the same. Yeah. So this is equal to 1 over root 2 times 5 centimeters per second, and 1 over root 2 times 5 centimeters per second. And so we can check that this is right, because we want it to be 5 centimeters per second total flow speed. So let's calculate what the modulus of that vector is. This is the square root of u dot u, which is the square root of the, so we have 1 over root 2 times 5 centimeters per second, 1 over root 2 times 5. Okay, so we take the product of the first two elements and then add that to the product of the second two elements. So here we get 1 over root 2 times 1 over root 2 is 1/2 times 5 is 25. We have centimeters squared per second squared. Plus, we get the same result from the bottom. We take the second two elements, multiply them. So again, we get 1/2 times 25 centimeters squared per second squared. So these two halves, we can combine them. So this would be just 25 centimeters squared per second squared. And then we take the square root, and we take the square root both of the value and of the units. And so the square root of 25 is just 5. And the square root of centimeters squared per second squared is just centimeters per second. So just a very simple example to set notation as to how we can define vectors that measure or that indicate current velocities, ocean velocities. We're doing this all the time. Everything's going to be some kind of current vector that arising from various phenomena, like waves or whatever. Okay. So very often, there's actually a, so very often when we want to write things that have different directions, it's helpful to use unit vectors as well. So I'll just introduce what the standard unit vectors are that we'll be using. Unit vectors. So these are vectors of length 1 that encode a direction only. So usually what we do, you can specify a unit vector that points in any direction. All that is required for it to be a unit vector is just that it has unit length. But usually, what we do is we use coordinate unit vectors. So we'll often use the coordinate unit vectors. And these are x vec hat, and this is the vector 1, 0, 0. And so here it's x vector, but then there's that little caret or hat symbol. That means it's the unit vector corresponding to the x direction. Y vector hat is 0, 1, 0, and z vector hat is 0, 0, 1. So if you have so unit vectors are very useful because you can write vectors out in a very useful way. That's in a bit of an expanded form. So any vector can be written in terms of unit vectors. So as an example, let's just take our vector from before. v3d is equal to 1, 0, minus 2. So that equals 1 times x hat plus 0 times y hat minus 2 times z hat. So we just usually write that as x hat minus 2 z hat. And if we had a general vector, so very often, this is actually some important notation here. When we are referring to a velocity vector, so whether that's for, say, wind, or whether it's for an ocean current, we usually use the notation u. Vector u is the complete vector velocity vector, and that has 3 components for the 3 directions, and we call those little u without a vector symbol, little v, and little w. So u is the east, little u is the east-west velocity component. Little v is north-south, and little w is up-down. And so this is notation that we're going to use very, very consistently. And whenever you see like a little u, you can always assume that that's in the east-west direction, little v north-south, and little w up-down. And so motion in the 2D horizontal plane just involves the u and the v components. Okay. Oh, and we could write this as using our unit vectors. We could write this velocity vector as u equals u x hat plus v y hat plus w z hat. Okay, so these are vectors. So we define vectors, dot product, coordinate system, x, y, z. So the next topic, which is one step more advanced, is the concept of vector fields. Can anyone offer a comment on what's the meaning of a vector field, or what? Not necessarily like a complete mathematical definition, but what does that mean? Does anyone know? So it's not a complicated idea. So when we think of a vector, we say like some particle has a vector momentum or something, right? So it's a particle that has momentum. There's a vector that exists at one point in space. So a vector field just means it's a function that says that at every point in space that there is a vector. So for example, if you think about this room, so if you think about the air in this room, so at every point in this room, the air has a particular temperature at each little point. There's some average temperature in here that's quite consistent, but over there by the window it's maybe a little bit different, by the door it's a little bit different, by each person it's a little bit higher maybe. And so we use the term temperature field to mean just the distribution of temperature over space and also over time. So a vector field is the same idea, except that that's what we would use if we were thinking about the velocity of the air. So at every point, as I wave my hands around or whatever, all of the little air parcels that make up this room, they're all moving around. Maybe not that much right now, but at every point you can assign a little local wind vector. I mean, here in this room right now the wind is very weak. But you could imagine assigning a mathematical vector at each point in space that tells you what's the velocity of the air at that point at that particular time. And that's what a vector field is. So, so a vector field is a function of space and time that assigns a vector to each spatial location. And so a very common, so the most common vector field we will deal with is the velocity field. So before we said we've got some vector, this is maybe the velocity at a particular point, like maybe you have a current meter. So a current meter is basically, it's essentially a little pinwheel that they stick in the ocean, and then as the current flows past the pinwheel, it spins it, and by measuring how fast it spins, you can figure out what the current was. And so this vector here, UVW, might be the three-dimensional current vector at the location of a current meter. But the velocity field is u of x, y, z, and time, and that's the three-column vector where each component also depends on the three spatial directions and time. And so, this we can sort of come across this in two ways. One way is you can be, and we'll do both these types of problems. So for some problems, you'll be given the velocity fields. We'll say, so let's say we observed the currents or we simulated them somehow. Then now, maybe we predict how does that transport material? How does it transport smoke particles or pollution or whatever? And then other problems, when we study waves, will be about calculating what the velocity field is from first physical principles, like in terms of forces and things like that. So we'll come across this velocity field idea all the time, and this is really the fundamental object. And when we get into the equations of fluid mechanics, we'll see that the velocity field is really the fundamental thing, the mathematical quantity we deal with the most, that really ties fluid mechanics together. It sort of captures how the fluid is flowing at every point in space and at every point in time. I'll say another vector field that you might be very familiar with, especially if you're coming from the physics side, is the electric and magnetic fields. So these are also, when you think of the electric field, it permeates space, and there's a particular vector arrow at every point in space that tells you which way the Coulomb forces are pushing. So the electric field, magnetic field, they're both other examples of vector fields. Okay, so when we encounter a velocity field or any vector field, the first thing that you usually want to do to try to understand something about it is graph what it looks like. And so you'll get a chance to do examples like this on the first homework. But I'm just going to do an example here now. So, okay. So let's consider the two-dimensional, we're going to say, sketch the following 2D velocity field. All right, so it's u of x of y, and in this case, I'll say it's I'll call it a steady velocity field, because in this case it's not going to depend on time. So maybe it's a snapshot. We have u of x and y, v of x and y, and I want to choose the particular formulas. U is minus y, and v is x. Okay, so so these are now meant to be formulas. So these are just really simple. It might almost be so simple it's a little bit confusing, but like this could be x squared or sine of x or whatever. So this is just the function x, the function minus y. And those give the east-west and north-south velocity components for this particular flow. And when you look at this flow, this formula, it probably doesn't mean a whole lot, but it means a lot more when you start graphing it. So what we're going to do is just draw our 2D axes here. So you have x and y. And now at each point in this 2D space, this function here, it tells us what vector to draw at every location. So I'm just going to pick the 4 points. Here we have 1, -1, and -1 here. So I'm going to pick, let's pick points. And these are kind of meant to be representative. X, y equals 1, 0, 0, 1, -1, 0, and 0, -1. Okay, so now we can draw a little table over here. So what's my value of u, and what's my value of v at each of these spatial points? We can calculate what those values are just by using our very simple formulas here. Okay, so let's take the first one here. So xy equals 1, 0, so that's this point here. So what's our vector? So x is equal to 1 and y is equal to 0. So y is equal to 0, so that means that our u component is 0. And x is equal to 1, so our y component here, our v component, is 1. And so this is the vector that points straight up, because this is the x component, that's the y component. So our vector points straight up with a magnitude equal to 1. Okay, so now we can try 0, 1. So 0, 1 is this point. So now x equals 0, so that means that our v component is 0. And y is equal to +1, so that means we have +1 here, so -1. So now this vector has a x component of -1 and a y component of 0. So this means it points directly to the left. So this vector will look like this. For our third component, we have x is -1, y is 0. So our y is 0, so our u is 0 here. And our x is -1, so that means our y component is -1 here. So now this is the vector that points straight down, because the x component is 0, the y component is -1. This points straight down. And for our last one, we have x equals 0, y equals -1. So x equals 0 means that our v component is 0, y equals -1. So we get -1 is +1, so we get a +1 here. And so this is the vector that points exactly to the right, because the x component is 1 and the y component is 0. So here's our final vector. And so if we sketch the rest of the arrows, what we would see is that they kind of look like this. And what this flow is it's actually a circular vortex. Vortex, by vortex we just mean any kind of flow that sort of goes around in a circle. There's not really a hard and fast definition of exactly what that means. In this case, we say it's a circular vortex, and it's also rotating in the counterclockwise sense. And I think, in the first problem set, there's a similar problem where you're asked to sketch a vector field that's going to look something like a vortex, and then comment on the directionality of rotation, how strong is it, etc. This procedure of taking a formula for a vector field and then sketching it in the 2D plane. Does anyone have any questions about that? That's a very, if this was confusing, it's worth it to take a minute to just pause. But was that okay? And you'll get more experience with this. Sketching is something that'll be for sure on both of the midterms and the final and the assignments. You'll have to sketch some kind of, usually fairly simple vector field. I wouldn't give some sort of complicated expressions that are hard to even calculate the numbers. The point is just to play around with very simple types of flows, like vortices being one of them. Okay. Okay, so that's it for vectors. And so now I'm going to talk about some reminders of calculus. Okay, so we'll start with okay, so the central concept of calculus is the derivative. So we have some function f of x, df dx is defined as the limit as delta x goes to 0 of f of x plus delta x minus f of x divided by delta x. So that's called the definition of the derivative. We learn this usually in Math 1000 or maybe in high school very often. And then we go beyond this definition and learn all kinds of rules, like the derivative of x cubed is 3x squared and stuff like that. But this is the fundamental definition. And actually, we're going to use this definition explicitly later on when we try to solve problems where there's no analytical solution. So it turns out actually that when you have a problem that's really complicated, the only sort of way to tackle it with calculus is to go back to this definition and then sort of execute the definition on a computer. That's how we calculate derivatives in many practical applications. So the meaning of this, so this is called the derivative of f with respect to x. And the meaning is if we have this function, here's x and some random looking function, then if we have some particular point here, x naught, then f prime of x naught, which is just another notation for df dx evaluated at x equals x naught, this derivative gives the slope of the tangent line right at that point where so it's the slope of the line that just grazes the function itself. Okay, in this course, we will deal with some problems that are one-dimensional, because you can think of, for example, flow of water going down a pipe in one direction. So it's just, there's not really any motion in the up or down or left-right directions. It's all kind of going in the x direction down the pipe. So we will talk about some problems in a single dimension that are very illustrative. But it's obvious that oceanography and meteorology and stuff like that occurs in the three-dimensional space. And so we had to go just a little bit beyond single variable calculus and incorporate functions of more than one variable. So this can be extended, this concept can be extended to 2 or more dimensions by defining partial derivatives. Can anyone remind me of what do I have to change about this equation? So let's say we have some function f of x and y. So what changes about the definition of the derivative so that it would be now partial derivatives with respect to x or y? Does anyone remember? if you're taking, now, have people covered partial derivatives before in a previous class? Yeah, okay. So does anyone remember the definition? It's a follow-up question.
It's like you treat whatever you're taking the derivative of, you treat the other one as a constant.
That's right, that's right. So this limit, so in the limit for the derivative with respect to a single variable, we sort of perturb that variable inside the function. We say x plus delta x. So we have our background x and then a little perturbation delta x. And then we're comparing that perturbed version of the function to its background value. And so when we do that with function of multiple variables, and we define partial derivatives, we just perturb one variable at a time. So we take a derivative in the x direction and a derivative in the y direction, and they're sort of totally separate. So for a function of two variables, we would have, for example, partial f partial x would be defined as the limit as delta x goes to 0 of f of x plus delta x and y unperturbed minus f of x and y divided by delta x, whereas partial f partial y would be the limit as delta y goes to 0 of f of x and y plus delta y minus f of x and y divided by delta y. And we'll do just we'll do a quick example or two. But so exactly as you said, the idea is you just treat whatever variable you're differentiating with respect to, you just do derivatives as normal, and every other variable you just treat as if it was a constant. So we can do an example here. So example, calculate the partial derivatives of the function f of x and y equals x plus 2y squared. Okay. Okay. Is anyone willing to take a crack at what's the partial f by partial x of this function?
2 times x plus 2y.
Correct. And how about this one?
4 times x plus 2y.
Correct. So you said 4, right? Yeah. So the way I would normally do this is you take down your 2, so you do 2 times x plus 2y, and then your chain rule, you pick up a derivative of this 2y, so that's 2, so you get 4 times x plus 2y. Okay, great. We'll be playing with all sorts of explicit models of flow. So you given some formula that describes a flow, you might want to compute some derivatives, gradients, etc. And so these rules are very handy. And all of the normal rules from single variable differentiation, like chain rule, product rule, quotient rule, those power rules, etc., they all go straightforwardly through to partial derivatives. Okay. Okay, so the last topic we're going to review today is Taylor's theorem. And Taylor's theorem is very, very important in every area of physics, but it's especially important in fluid dynamics, and it's used over and over when we derive the laws of fluid dynamics. So, Taylor's theorem. And these are also called Taylor series. And you might have seen something called Maclaurin series, which are similar. Can anyone tell me what's the general idea of Taylor's theorem? Like, what's it about? Like, what does it do? Or Taylor series? Like, any information about it at all?
You take your function and you rewrite it as a polynomial series as opposed to just some weird complex function.
Whatever function it happens to be. Rewrite it as a polynomial. That's good. Any other? That's like structurally. That's what it is. You rewrite any function as a polynomial. is that polynomial, is it meant to approximate, so it's meant to approximate the function? Or, so I guess my question is, so do we generally expect, if you have a Taylor approximation of polynomial, that that's equally accurate everywhere? Or is it more accurate some places than others? Maybe a bit of a weird question. So the key idea is that the Taylor series is a polynomial approximation to any function, and it's meant to approximate a function very well near a particular point. So you choose a point in space, or let's say a value of x, and then you expand in a Taylor series nearby to that value of x. So the statement of the theorem, sort of the simplest version, is that f, for any function f, f of x plus delta x is equal to, actually, so x naught. So let's imagine we have some function. There's some particular value, x naught. Maybe we're interested in how, let's see, sea level. Let's say we have on the x-axis we have carbon dioxide emissions, and on the y-axis we have sea level. So there's some kind of complicated relationship between these two things. But we might be interested in knowing, let's say our current, whatever it is, 430 ppm or whatever, current CO2 levels. And we might be interested in saying, well, the whole curve is maybe complicated, and it might have physics that's not at all relevant to our current situation, because there might be, a particular relationship might encode physics that's very, very different from the circumstances that you find yourself in on Earth, for example, right? So there's so something happens to sea level when CO2 gets very, very, very low, but that's not really relevant to us. It's at some fixed value or what's going on. So what we often want to do is take some complicated function that might have divergences and all kinds of bad stuff happening, and just approximate it locally near a particular point of our choosing that's chosen because it's relevant to the problem we're interested in solving. So we want to say, like, maybe maybe take a linear approximation like that, or take a quadratic approximation like this, and basically approximating it by a line is a first order Taylor series. Approximating it by a quadratic parabola is a second order Taylor series, and you can construct higher and higher polynomial approximations, cubic and so on, using Taylor theorem. And so the statement of the theorem is that if we have some point x naught, that's our central point that we care about, and we ask, what is the value of f, not at x naught, but at a nearby point? So we take some small delta x. We'll say nearby to x naught, at x naught plus delta x. So maybe x naught could equal 1, and then delta x could equal 0.01. So we're considering f of 1.01. And the idea is, if we know f of 1, and we also know df dx at 1, and we also know the second derivative of x at 1, and we know all of the derivatives of the function at this particular central point, x naught, or in this case 1. If we know all of those derivatives, that actually encodes enough information that we can reconstruct the whole function. And so the formal statement of the theorem is that f of x naught plus delta x, so a little bit away from x naught, is given by the value. The first term is the value at x naught. So it says if we've only shifted a little bit, first of all, the function hasn't changed that much. It's just our background value. Well, then plus, there's a correction term that is delta x multiplied by df dx, and that's always evaluated at x naught. And so this is a linear approximation. So that's like plotting our line, and we'll show how that exactly works. And then there's higher order terms too. So there's a term like 1/2 delta x squared times the second derivative evaluated at x naught. And then there's a whole infinite hierarchy of higher order terms. And what I've done here is I've written this a sort of weird notation. This is not a 0, it's a big O. And this notation is literally called big O notation. That's the technical term, really. And so what this means is that all of these, there's a whole bunch of terms here, but all of them depend on delta x to at least a cube factor. And why that matters is, we're always thinking about delta x as being small. So let's say delta x is 1 over 100. So now delta x cubed is 1 over 100 cubed, which is 1 over 10 to the 6, so 10 to the minus 6, so 1 over a million. And so these terms are very, very small, whereas these terms up front are less small. So the first term might be proportional to 1 over 100. The second term is 1 over 10,000. Third terms are 1 over a million, and so forth. So what we always do is there's actually, when you take Math 1000, there's a whole formal version of this theorem that includes all the terms. I remember there's this particularly gruesome result called the Taylor series remainder theorem, which I remember being very hard to understand. So there's a whole formal theory of this that treats all of the terms in infinite series and so forth. But what we do in physics almost universally is we only care about the first two terms here. So we take the background term, the baseline level, the value of the function at the point that we know, plus a term proportional to the first derivative of that function. And then what we usually do is we just replace this equal sign with an approximately equals, and we say f of x naught plus delta x is approximately equal to f of x naught plus delta x df dx at x equals x naught. And this is the first order Taylor series approximation to the function f. And this is so useful that it's hard to overstate how useful it is. If you go on to do anything in sort of advanced engineering or physics, this idea that the key idea of this, right, is that if you look at this graph, if you zoom in, imagine blowing it up and blowing it up and blowing it up. You zoom in near this point. When you zoom in enough, everything looks like a straight line. And so if your delta x is tiny, so that you're only moving a little tiny distance from your background point, then you can treat everything effectively as a straight line. And the Taylor series tells you what straight line it is, the exact formula for that straight line. And this is incredibly useful for deriving laws of physics, because usually, and by usually I mean pretty much always in physics, everything happens locally. So we even have like principles in physics, like special relativity. Like two things can't happen infinitely far apart and influence each other. There has to be like a contact happening. So in physics, every object influences every other object locally, so at the same point in space. And so very often, we can, if we want to consider the interaction between two objects that's happening very near each other in space, we can treat basically everything as a straight line by using this physicist's intuition that when you zoom in on any curve, if you keep zooming and zooming and zooming, eventually it becomes straight. Okay, all right, so that's it for today. So I will see everybody on Thursday, and then the schedule for the course, I think, is that the first assignment, I'll post it on Friday, but then it's mostly math review. But then you have another 2 weeks to do it, so you won't. All the material probably won't be covered by Thursday, but it won't be long after that. If you have any questions or anything like that, or also if you're interested in research opportunities, please feel free to reach out. And other than that, I'll see everybody on Thursday.
Thank you.
You're welcome. And this first lecture is extremely dry for this math review. It's a lot more physics-based and fluid concepts.
Just wanted to get access to the grade space.
Oh, no problem.
Do I need
Yes.
to send you anything for that?
No.
No?
No, I think, because yeah, I had your email. The only thing I need is your money email, but I have that already.
Okay.
Yeah, no problem. So just one question is, so how come you're not taking the course? How come you want to audit it?
I don't know.
Because I'm already taking 5 courses this
Okay,
semester,
yeah, okay.
and I don't have time to do 3,300 to do 4,300.
Oh, oh.